Ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at density of gases and how we're going to use the information if we're ever given the density of a gas, or we want to determine the density of a gas, and how we do that, how we figure that out, how it relates to some things that we already know. Okay, so first off, I'm going to draw a couple of balloons here. And let me make it a little bit bigger than that. I want to write inside of it. All right, so there we go. There's one balloon, there's two balloons, there's three balloons. Now, those balloons are supposed to be the same size. Those balloons are all at standard temperature and pressure conditions, which means 1 atm and 273 degrees Kelvin. Okay, so, and what we've got here is I'm just going to go ahead and tell you that these are all 22.4 liter balloons. Doesn't matter what's in it. Right? Because if at STP, if it's 22.4 liters, I have a mole of gas in each one of them. And so I'm going to say 1 mole, and 1 mole. So nothing too crazy for you yet. But now what I'm going to do is I'll go ahead and tell you the gas inside of this balloon is oxygen. The gas inside the middle balloon is hydrogen. And the gas in the third balloon is ammonia. All right? So now, what does that do? What happens here? And what's the difference in density of those particular balloons? Because they're all the same volume. But remember, density is actually a mass per volume relationship, right? And so we all understand that 1 mole at 22.4 liters, but I look at the formula mass of these and ask the question, well, how much does 1 mole weigh? Well, 1 mole of oxygen weighs 32 grams. 1 mole of hydrogen weighs 2 grams, and 1 mole of ammonia weighs 17 grams. So now, what are the densities of my particular balloons? Well, this one's 32 grams over 22.4 liters, right? This one is 2 grams over 22.4 liters, and this one is 17 grams over 22.4 liters. So even though the number of moles is consistent and the same, the volume is the same because I'm at standard temperature and pressure, the density of all of my gases is different. And so this can become important when we're trying to collect gases in a reaction. If there's a difference in density, maybe the gas will not escape from the container that it's in, right? Because gas is a fluid. It's fluid by nature, and so just like your liquids at different densities will layer on top of each other, gases will do the same thing, all right? Okay, now, how are we really going to use this? How can we use density to calculate and determine some of the variables that we want? Well, believe it or not, this actually goes back and relates back to Pivner. You had to know it was true when we started up here talking about 1 mole, 22.4 liters. That had to be your lead-in to the fact that we were going to do stoichiometry. Plus, we were talking about standard temperature, pressure conditions. What if we're not at standard temperature pressure, but I know the density of my gas when it is at standard temperature? How do we do that? Well, yay, hooray. Here comes Pivner. Okay, so what I'm going to do is I'm just going to go through a real quick derivation with you about how we get from Pivner to use density and actually be able to plug in density into this particular case. A couple of things I need you to keep in mind. Right? Mass divided by volume equals density. And the number of moles, remember, is your mass in grams divided by your molar mass. All right? Okay, so I'm going to use this first. I'm going to substitute that in for N. So I end up with PV equals mass over molar mass times RT. Right? I'm going to multiply both sides by molar mass. Right? And so that cancels out over here. And then I end up with molar mass times PV equals, actually it would be mass times RT here. All right, and then I'm going to move PV off to both sides, right? Cancels off there, and there we go. And this is where we're actually going to start working. So I've got mass times RT divided by pressure times volume. Well, if you recognize this relationship here, that's actually my density. And so what this relationship becomes is that the molar mass of a gas is equal to the density times my gas constant times temperature divided by pressure. All right? And so this is how we're going to be able to use if we're given a particular density, as long as it is in grams per liters, right, is what it needs to be if it's going to plug into this particular equation. If they'll try and trick you sometimes, ladies and gentlemen, they'll give you your density of a gas is something besides grams per liters. You just need to be able to convert it to grams per liters before you plug it in to this particular formula, all right? And then the easy way to remember this is actually molar mass kitty cat. Is a friend of mine named Renee McCormick actually taught me this kind of little memory trick with this. So molar mass kitty cat, and if you actually look like this, then she said that the MM looked like ears on a cat. And I mean, I guess, but it for whatever reason, the phrase that she gave after that is what really stuck in my mind. All right, so molar mass kitty cat, and what she says is that every good cat puts dirt over its pee. All right, so you've got dirt over pee. Crude, yes, she would say. Effective, you betcha, right? For whatever reason, this is something that has stuck with me for quite a long time, all right? So it's an easy way to remember if you're ever given the density of a gas in a stoichiometry problem and asked to do something, calculate the number of moles, calculate all these different kinds of things, calculate pressure, calculate temperature, then we can actually figure that information out. It's related to Pivnert, which means we can definitely relate it and use it in stoichiometry as well, all right? So hopefully, if you got any questions, you got them down. I'll see you in tutorials for those. Otherwise, I will see you in class.